I don't see any gears turning. I don't hear any steam coming out of your ears or anything like that. There may be a couple good answers, not just one answer. I know this is a great hashing function because well, that's a good answer. I was expecting that good answer. I know it's a good hashing function because when I use the same names and I hash them in, before I got 12 collisions and now I got 7 collisions. So I think it's better. Is that a proof? No. Is it definitely better if it got 7 and another one got 12? Is it definitely better? No. And the reason it's not definitely better because it's only better because you use the same set of names for the 12 and the same set of names for the 7. Maybe those names are not representative of what you're going to get in the future. So you don't really know if it's better. It appears to be no worse. Right? Maybe it's better. That's an observation. So I want something that would describe the great function from the probability standpoint. So forget about the results. Let's talk about, we want to write a hashing function so that what happens? This is the hard question. What would a perfectly designed hashing function do with respect to probability and the hash table slots? And the answer is the perfect, and don't confuse the perfect hashing function with perfect hashing, which is when you allocate one per each record guaranteed. That's the way we did at the beginning. What I mean by perfect hashing function means the best possible hashing function. The best we can hope when we are going to have a situation where we're going to have potential collisions is we want the hashing function to target every single slot in the hash table with equal probability. That's the best we can hope for. We want our hashing function designed in a way that the probability of any one of the slots in the hash table has an equal probability of coming up. We want a hashing function which will uniformly distribute the keys across the table and not lump them into one area or one slot and collide, or into a few areas. We wanted to uniformly distribute the keys across the hash table so that the probability for each hash table slot is the same. We don't want so-called popular hash table slots. It's not good. We don't want popular slots. We want to have equal likelihood. Okay. So we'll come back to that because that's a probability issue. We don't know the keys in advance, so we have a chance of two keys colliding. It's always going to happen. If you have a collision, does that mean that your hashing function is not excellent? Absolutely not. And I'll tell you some very, very bad news. If you don't design your hashing properly, but you design an amazingly good hashing function, let's say you have 1,000 slots and 1,000 records, and you put them through the best hashing function you can possibly design. That's one that targets each slot with equal probability. The fact of the matter is, you can still expect that, roughly speaking, about 37% of the slots will not get a single record going to it. Not a single record. You got 1,000 slots. 368 slots are statistically not going to have any records hashed to them. But it doesn't matter how good your function is. This is the perfect function. That's an unbelievable observation. Well, I'll come back to this later and say, why is it so bad? Is hashing always so bad? No. But there's something in there that was quite bad. The hashing function itself was wonderful, but there was other problems in the problem that I presented to you. But the fact of the matter is, the nature of hashing is that you have to know a lot about how to do it. And by the way, hashing is not limited to gigantic files. Hashing is used all the time in memory for directly looking something up. So you can have a hash table for, in fact, many languages like Java, like C#, even C++ have built-in structures, abstract structures that actually create hash tables and mapping. In C++, that structure is called a map. How many people know C++? Have you ever used a map? So you know what I'm talking about. So a map has two entries when you put or get. So when you put, the key is the first parameter, and the second thing is the value, whatever it is the object. So it hashes on the key. Java has the same thing. It has a hash table. It's called hash table. But it also has other implementations of hash table. It has something called a hash set. Anytime you see the word hash in a structure, it's using a hashing algorithm. And of course, all of those are in memory. So you may have, for example, a hash set of 1,000,000 elements. And so the way the language finds the hash set in Java is basically hashes on the key to immediately get to the element. You are not even seeing the hashing functions. But in some cases, you might want to do your own hashing functions, and we're going to be talking about hashing functions too. How to design them, what to look for. All right. So, we do not know what the keys look like in advance. We have a real chance of two keys colliding in the hashing function. We need to know how to handle collisions as part of the hashing strategy. One approach is called linear probing. Linear probing is very, very easy. So you have a hash table, let's put it like this, hash table, you get all the slots. So let's say somebody hashes, they go right in here. Another one hashes, different key, goes same place. There's a collision. So that's index I. So now we say, well, wonder if index I plus 1 is available. It is. That's where it goes. It's not. How about I plus 2? How about I plus 2? Okay, we're just gonna linearly go through the array in a cyclical fashion until we find a spot. That's called linear probing. That's a resolution to a collision. How can we improve hashing? Well, we can improve or increase the table capacity. If the hash table is made larger and the hashing function has an equally likely target of any one of the locations, then the probability of two going to one location would be decreased. Doesn't that make sense? If the table is size 100, then what's the probability of any one slot being selected with equal probability? 1 out of 100. So that means the probability of 2 is going to be 1 over 100 times 1 over 100, 1 over 10,000. Okay. What if I make the table 120? What's bigger? And if the hashing function, again, is equally likely targeting all locations, then the probability is not going to be 1 over 120 squared. So it's going to improve over the collision probability with the same type of quality function. We can try to resolve collisions in a different way, or perhaps even use a different hashing function. Increasing table capacity may reduce collisions, but it will definitely not eliminate it. Here's a very interesting analysis that should ring a bell for you. A table with 365 slots or locations and 23 random keys will have a chance of higher than 50% of at least one collision. We're talking about 23 keys and 365 slots. greater than 50% chance of a collision. Anybody know why? This is a problem that we talked about in this class, I think. We talked about the birthday paradox in this class? No? No. Well, I'll talk about it now. This class is too small, that's why I don't like to do the birthday paradox. But the birthday paradox says that, notice that there's approximately 365 days in a year. I know we can argue that extra day, but anybody here born on that extra day? What's the probability of that? Never. All right, so a table of 365 locations, think of them as a day. And now we're going to choose randomly 23 people. We'll call them keys. And we'll ask them for their birthday. Each of their birthdays will map to exactly one of those spots. There's a 50% chance that two people that we choose out of 23 are born the same day. They're going to go in the same spot. That's going to be a collision. There's a nice way to show it through probability, and again, if I increase 23 to 33, 43, 53, and I keep this at 365, the number of collisions is just going to jump like crazy. Another important quantity with hashing is something called packing density. Packing density is a very simple idea. So you have a table. Let's say it's this much. Now, I know that the records are going to go everywhere, but let's just compress the records. So this is my table, how much space I have. Let's say that all the records have this much space. They're different places, but they take this much space, which means that this much space is not used. So the packing density is simply the part of the hash table space which is being used for records. Okay? So it is simply the percentage of the hash table space used to store the data. So it is a number which is between 0 and 1. If the packing density is 60%, that means that 40% of the hash table is not utilized. If it's 80%, then 20% is not utilized. 1 minus, right? Why would we want the packing density to be low or high? What's the advantage? Well, if the packing density is low, then we are really doing that for what reason? We lower the packing density in order to reduce collisions. And we increase the packing density in order to You're 2 for 2. There's a single, there's a double with a gap. All right, so 2 for 2. So yeah, so we lower the density to reduce collisions, and we raise it to maximize memory efficiency. Clearly, we're talking about this direction, and then we're talking about this direction. So really what we're looking for is a sweet spot. We want to lower it enough so the collisions are minimized, but what's going to happen, what do you think is going to happen if packing density goes lower and lower and lower? Collisions are decreasing, but what do you think is going to happen? The rate of decrease is getting smaller, smaller, smaller. Initially, they decrease like this, and then they decrease like this, so it's almost not worth it. So, it turns out that the packing density between 60 and 80 is considered to be fairly optimal. Obviously, 60 would have less collisions, and 80 would be more efficient memories. Another interesting technique for handling collisions is to use chaining. And chaining is a way, not necessarily to handle collisions in any special way, but basically we treat the entire hash table rather than a place where we store the value of the records, then the keys. we simply store a linked list. So if somebody hashes to index I here, they simply get appended at the back end of the I chain. So for example, remember the records 73 and 273, which went to the same location, which was, I think, 23. So chain 23 would have 23 and then followed by 273, because they both hash there. So rather than doing like linear probing or some other technique that we'll talk about, we basically expect collisions, some amount of collisions, and we create chains of records that hash to the same location. Now in this case, it's interesting that we no longer have to really think about packing density so much. So if we're going to have, let's say, 1,000 records, then we could simply, typically use 1,000 chains. Keep in mind that 368 of those chains will be completely empty. As long as we use the best possible hashing function, it could be worse. So that's very interesting. So 368 of those chains are going to be empty, but the other 1,000 minus 368 will have at least one record in their chain. Some will obviously have 2 or 3 or 4 maybe, or even probability says 5 or 6. So that's chaining. So we'll come back to that also. Another type of resolution technique is called quadratic probing, very similar to linear probing, but on a collision, rather than going linearly trying to find the next available slot, if we collide here, we go I plus 1 squared, I minus 1 squared, I plus 2 squared, minus 2 squared, minus plus 3 squared. So we're going to take quadratic jumps. If the jump becomes too high, then it wraps around. So we have a modulo function. So we're going to multiply it by k at k squared, and we'll take the whole value modulo size of the table. So we're going to get someplace. And the reason I might do that, anybody know why that might be a better idea than linear probing, quadratic probing? One of the things that it'll do, it will prevent records that are colliding in a similar location for basically making a big blockade for other records. Remember, every time you have a collision and you resolve it using linear probing or quadratic probing, you're taking up a slot for another record that wants to hash. So if I hash to I and I collide and I go to I plus 1, the record that really wants to go to I plus 1 collides with me, even though I don't belong there, but I moved there. Every time you search for me, you get I, and you don't find me. So now you have to go to I plus 1 to find me. Okay. Let's go back to chaining. So this is what the idea of chaining is. So what we want to do is we want to look at the basic average analysis of hashing implemented with chaining. So here's what we're going to assume. We're going to assume that we have a hash table with m locations. By m locations, I mean m chains. And we're going to have n entries. Now notice, it's not a problem for us to have n, the entries, being greater than m, because we simply will assume collisions are going to be handled by chaining. So therefore, it's possible for us to have multiple elements in a chain. We're still hoping that a great hashing function will select each of the chains with equal probability, and that's why the probability I use here is 1 over m. If there are m locations and m chains, then each chain has the probability 1 over m of being selected by the hashing function. Each list, starting with list 0 to list n minus 1, has a length. That's the number of elements currently in that list, in that chain. And we'll assume the probability, every list is equally likely outcome of a hashing function with a probability of 1 over m. So the average complexity of an insertion at the back of the list, let's think about what that means. In order to have the average complexity of being inserted at the back of the list, first of all, you have to hash to a location. It's called I. That is going to be a list. So we'll have to go through that list to find out that the key that you're trying to insert is not already in the list. because that would be a duplicate, so we're not going to allow duplicates. So we're going to hash, then we're going to traverse that chain. And if every element in there is not matching you, then we're going to append you to the end of the list. And that's what I mean by complexity of insertion at the back of the list. So the average complexity will be the summation through all of the chains, multiplying, this is hard to see, pi times ti of n, where pi is the probability of a chain being selected, multiplied by ti of n, which is the number of comparisons in the ith chain. Well, we know that the probability of selecting the mth location is 1 over m, or any location, the ith location is 1 over m. So that is a constant that can come out in front of the summation, and we know that ti of n is the number of comparisons in list I, which will be the length of list I. And since we're summing now the length of list I, the length of list I, as I goes from 0 to all the lists, will be the summation of all the elements in the list, which is n. Therefore, my complexity, average complexity of adding an insertion at the back of the list is n over m, where n is the number of records in the hash table and m is the number of lists. Now, if m and n are close to each other, then we say the average complexity is big O of 1. Does that make sense? The average complexity of an unsuccessful retrieval. We fail to find the key in the list returned by the hashing function. So we hash, it says, okay, it's list I. We compare every single value of list I. And we fail. What does that mean? Well, it means that we have to inspect every element in list I. So the list, every list is equally likely to be returned by the hashing function. Therefore, our analysis is exactly the same as for insertion. Because notice here, we basically just counted the list I. Well, in order to fail to insert, you have to go through the list I completely with equal probability for every list. Therefore, the summation is going to be n over m again. And again, if they're close to each other, we're talking about big O of 1 complexity. Let's talk about the average complexity of a successful retrieval. A successful retrieval. We're going to insert keys at the back of the list, and the complexity, if we insert at the back of the list, then the complexity of a successful retrieval is 1 more than an insert. Let's think about that. So imagine the list right now, the list at index I has 3 elements in it, 1, 2, 3. Okay. So now I have to, and let's think about the element that I inserted that became the 4th element. I'm going to insert that element. So the element hashes, it goes to list I. I check the first one, not a match, not a match, not a match. I insert it. Okay? How many comparisons did I make? Great. Now I'm going to retrieve it successfully. So it's going to be a successful retrieval. So I'm looking for the key. I just inserted it a little while ago. It goes to list I. I compare, miss, compare, miss, compare, miss, compare, hit. So the average retrieval, basically, 1 more operations than for the insertion of the very same element. That's what I'm saying here. So, so what we're going to do is we're going to consider the jth entry into the hash table. Jth entry into the hash table means I'm inserting elements into the hash table using chaining. I insert the first one, it goes to a chain. Second one goes to a chain. Third one goes to a chain. Finally, I am inserting j minus first element and it goes to some chain. So now I have j minus 1 total elements in the hash table. And now I am going to insert the jth entry. The average cost of its insertion is going to be j minus 1 over m. That's because each of the m chains is equally likely. That's 1 over m. And j minus 1 is the total number of elements in the entire hash table across all the chains when the jth element goes in. Therefore, we take those j minus 1 elements and we divide them equally across all the lists. So therefore, the average cost of insertion is j minus 1 over m comparisons for the insertion. Therefore, for the retrieval, it's going to be the same thing plus 1. So that's what we're going to have. So the retrieval cost is going to be j minus 1 over n plus 1. And now we're going to look at the average of all possible successful retrievals. That's going to be average complexity. We're going to sum all of the successful retrievals, and we're going to sum for j equals 1 to n. So j is the retrieval cost of the jth element. We're going to find that average cost across all n elements. So we'll take, j is going to take the values from 1 to n. And we're going to use this cost here and use that one. Of course, it's going to be 1 over n, because it's going to be n elements. So we're going to have, this is going to be 1 over mn times the summation. Okay, and then finally, we're going to come up with n minus 1 over 2m plus 1, which again, if m and n are close to each other, we're talking about very close to theta 1. So chaining appears to have a good performance. We can do further analysis of that, and we will later. And the average complexity of a successful deletion is the same as a successful retrieval. Okay, so that's kind of where I want to leave it with chaining. We're going to come back and do some more detailed analysis of hashing and the probability of what can happen later on. But what I want to do right now, the time that we have left, which is not very much, is to just talk about hashing functions in general, how people construct hashing functions. So I'll go through this quickly. You can look at the notes and check this out. So let's say we have a name like Joseph or Thomas or Adam or Melvin, whatever. So what we're going to do is we can break this name, for example, into its characters. And so we'll use 74 for J because it happens to be the 74th ASCII character. O, it happens to be the 111th. So if I multiply them by each other, I'll get a crazy number. We like crazy numbers. And then what I'm going to do is I can do something like a modulo if I want to. And that modulo can give me some kind of a number. So notice that in this case, I'm just doing a division by the remainder over 1,000. So it's 214, 324, 500, 777. Does that make sense? Okay, so it looks pretty good. So names are going all over the place. So this type of function will give me how many different hashing values? 1,000, right? 1,000. So I'm taking the last 3 digits, decimal digits, so it's going to be 1,000. So what makes a good hashing function? One that has any key mapped to any location with equal probability. We mentioned that. Why is our previous example not a good hashing algorithm? Why is this a bad hashing algorithm? It looks pretty good, but actually it's terrible. And the reason it's terrible is because JO is good for Joseph, but it's also the same as John, Joanne, and what's the probability of how many names out of the typical names in the United States starts with JO? I don't know. But I bet you it's more than start with ZZ. Okay, so probably using just those two is going to have preponderance of names, or a lot of different names hashing to the same location. So maybe we're not using enough of the key in this case. So generally the hash table should be larger than needed. For n keys, we should have n times k slots, where k is a large number 1.0, obviously. If k is 1.0, we would need perfect hashing to map the keys to the hash table without collisions, and we know that's not practical. Hashing without collisions, and I don't know about this number, I came up with it a long time ago, and I forgot where I came up with it, has been shown to be practically impossible with a probability of 10 to the negative 120,000 power, providing no collision of hash solution. Now, I can come up with this number again, I just don't have the data for it right now. But it will not take a lot to come up with a number as unlikely as that. Okay. We might say, what is the probability? It's almost like saying, where's the probability of having 365 slots in a hash table and randomly selecting people so that they each have unique birthdays? I wonder what the probability of that's going to be. I'll tell you what it is. It's unbelievably small. It's so small, it's just not going to happen. You can bet on it not happening. If you bet against it, you're going to have a problem because the probability is so low. And we can find out what it is. How would you get the probability? Well, if the first person, I'm going to select one person, what's the probability that they're going to be a unique birthday, the first person? Guaranteed, because there's no other birthdays. So I'm picking now a second person. So what's the probability that they are going to have a unique birthday? Well, there are 365 days, let's say. So 364 of them are good. So 364 over 365. Okay? Now I have two people with that probability that have unique birthdays. Now a third person comes in. How many birthdays do I have left? 363. So it's going to be 363 over 365. 362 times 365. 361 over 365. 20 over 365. 19 over 365. 18, 17, 16, 1 over 365. That's the probability. Figure it out. All right. So a good hashing algorithm should do a lot of randomizing. It's a good idea to use a big part of the key for this process. So JO is not enough of the key. If the key is going to be the first name, use more of it. But probably, I think we need more key. JO, even if just the first name is not so good, because if somebody's name is John, right? Or somebody's name is, what's your name? Gayatri. Right. How many Gayatris do we have? So many, especially in India, right? Mm-hmm. So you don't want to use just your first name, because then everybody's going to be colliding with you. You don't want that. Okay. So lots of different ideas we're going to look at. So for example, one thing is something called folding. So for example, if you break out the name and you look at all the ASCII characters underneath it, notice that some keys are going to be shorter, in which case we can just put blanks in here, which is a 32 ASCII character. This is an idea of folding that we can create. So for example, for Joseph, what we could do is we could use 74, 111. So basically, we're going to create a number by simply not adding them, but folding them. So it becomes 74,111, 115,101, 112,104. We're going to create these crazy numbers by adding them. Then we'll actually add these three numbers and come up with 301,316. And then what we'll typically do is we'll divide that number by the size of the table, or perhaps by some large prime number. Prime numbers are very popular because they tend to have an equal probability when dividing properly. So in this case, what we could do is we could take these large numbers and do a modulo of this large prime, again, add those together, and then you come up with this. And then again, you can take this and divide it by another large prime, and that will give you a better distribution. Okay? All right, I think it's time to stop. So let's say today's Wednesday.